You ever stop and think about the last time your banking app or your favorite social media feed actually went down for maintenance? You probably can't even remember, right? Well, today, we're going to pull back the curtain on the engineering magic that makes that seamless 24/7 experience possible.
I mean, this is the big question, isn't it? It's the multi-million-dollar problem that every single successful tech company has to solve. How do you keep the lights on all the time for everyone, everywhere on the planet? Today, we're going to break down the core engineering principles that keep our digital world turning.
So to really get the solutions, you have to appreciate the problem itself first. And it's a set of really tough competing demands that we're calling the modern apps dilemma.
And look, you got to understand, these aren't just nice-to-haves anymore. Nope, they are the absolute table stakes for any serious application today. You have to be fast, you have to be always on, you have to be constantly getting better, and you have to be accessible from anywhere. That is a huge ask.
And this just nails the core problem, doesn't it? It's this constant tug of war. Change, introducing new features, often breaks things. But you need 100% availability. So how do you swap out the engine of a race car while it's still speeding around the track? That's literally the challenge engineers are facing every single day.
Okay, so how do engineers even start to tackle this monster of a problem? Well, the first, most fundamental piece of the puzzle is this really clever architecture designed for both scale and for safety. It's called the primary-replica system. Think of it like this. The primary database is the original master blueprint. Any changes, any new information, it has to happen there first. That's how you keep things orderly. The replicas? They're like perfect, certified, read-only copies of that blueprint, handed out to everyone who just needs to look at it. This simple idea is incredibly powerful. So why does this matter so much? Well, first off, you can handle a bazillion people looking at the data, that's what we call scaling reads, without ever slowing down the master blueprint. Second, if that primary server ever fails, you can quickly promote one of the replicas to become the new boss. This whole process, it's called a failover, and it's the key to high availability. And finally, because there's only one place making changes, it's way easier to keep all the data consistent. Okay, so this leads to a really big decision. How do those copies stay perfectly in sync? On one side, you've got synchronous replication. Think of this as the super careful, by-the-book approach. The primary actually waits for confirmation from its replicas before it says, okay, job's done. It's definitely safer, but all that waiting adds time. On the other side, you've got asynchronous. Here, the primary just yells, hey, I made a change, and immediately moves on. It is blazing fast, but it does carry a tiny risk that a replica might not hear the news if the primary fails right after shouting. So, what is this messenger system that's broadcasting all the changes? How does the primary actually talk to all its replicas? Well, it all comes down to a component that acts kind of like the system's own indestructible black box recorder. And boom, here it is, the write-ahead log, or just WAL for short. Before the database ever touches its main data tables, it first writes down exactly what it's about to do in this special log. This is what makes it the ultimate source of truth. If the whole system crashes mid-operation, the WAL knows exactly what was happening and can pick up right where it left off, perfectly.
The process itself, it's actually beautiful in its simplicity and its safety. A transaction starts, the intended change gets written to the wall first, and only then is it actually applied to the database itself. This log-first principle is the absolute bedrock of modern database reliability.
So if the wall is the source of truth, how do we get that truth out to everyone else? That's where this cool thing called Change Data Capture, or CDC, comes into play. It's basically a process that just sits there reading the log, and it sees every single change as it's written, and then streams it out to anyone who needs it, like our replicas or maybe a totally separate analytics system. It's a brilliant way to untether the database from everything that depends on it.
Okay, so we've solved for massive traffic and for system failures. But what about that other huge requirement, evolving the system? How do you change the very structure of the database, what engineers call the schema or the blueprint itself, without shutting everything down for maintenance? The answer is this incredibly disciplined four-step dance. First, you expand. You add the new column or table you need so the system supports both the old way and the new way. Then, you migrate. You slowly copy data into that new structure, in the background, while the app is still running and using the old stuff. Next, you switch. You update the application to start using the new structure. And only when you're absolutely sure nothing is using the old way, you contract. You clean up and remove the old schema. And right there, that's the secret. You know that new feature that just magically appeared in your app overnight? Yeah, It wasn't magic. It was a carefully orchestrated expand, migrate, contract process happening completely behind the scenes, making sure the application never, ever missed a beat.
All right, for our final act, let's tackle the biggest challenge of them all, moving an entire live database from one side of the planet to the other. This is the real high-wire act of database engineering.
And why on earth would you even attempt something so risky? Well, for a few huge reasons. To get your data physically closer to your users for a much faster experience, to comply with local data laws like GDPR in Europe, or to have a complete backup ready to go in a different part of the world just in case of a major disaster.
The plan for this has to be flawless, executed with surgical precision. You use that same CDC mechanism we talked about to start replicating everything to your target region. Then comes the really tense part. You watch the replication lag, waiting for the exact moment it gets to nearly zero. For the briefest possible window, we're talking seconds, you pause new writes, you switch all of your application traffic over to the new region, and finally, you promote that replica and it becomes the new primary. It's a high-stakes, super-coordinated switch that, when you do it right, is almost invisible to your users.
So as we've seen, none of these techniques is a silver bullet, right? A simple primary replica system is time-tested, but it can create a write bottleneck. Synchronous replication gives you that rock-solid consistency, but it adds latency. Asynchronous is fast, but it carries that small risk. And a CDC-based system is incredibly flexible, but it definitely adds more complexity to the whole setup.
So here's the crucial point, the big takeaway. There is no single best architecture. The right choice always depends on the specific needs of your business. Do you need the absolute ironclad guaranteed consistency of a financial transaction? Or do you need the blazing fast performance of a social media like button? Your answer to that question determines your architecture.
And this quote just brings it all home, doesn't it? Replication is all about surviving the present moment, keeping the lights on no matter what. Migration is about evolving for the future, allowing for change. You absolutely cannot think about one without the other if you want to build a system that's truly built to last.
So, we've seen how modern systems achieve what really seems impossible. These principles of replication and migration, they're the very foundation of our resilient, ever-evolving digital world. The only question left is, now that you know the secrets, how are you going to build your next unstoppable system?